Today we're going to look at 9.9, representing functions as power series. Now we already talked about being able to represent some functions as a power series. In fact, last section we talked about e to the x. You can see an infinite series here. If I represent it as a summation, so the summation is n goes from 0 to infinity of that x of n over n factorial. This one is actually convergent everywhere, and it's the exact series that represents e to the x. We're going to see how to develop this type of series next section when we do the Taylor and Maclaurin series again. But now we're going to see them as an infinite series, not just as polynomials. But there are other ways besides using Taylor and Maclaurin to represent series functions as series. And there's one specific way that we're going to use in this section. For instance, if I have the function f of x equals 1 minus x. Well, let's back up to pre-calculus a little bit, or something we did earlier in this chapter, and let's talk about a geometric series. We know that a geometric series has some first term a times a radius r raised to the n. And if we expand it, you would see that every term is multiplied by an r as you add to it. And we also learned that the sum of this, this summation, we had a formula for that. It was one of the few infinite series that not only can we talk about convergence and divergence, we actually were able to find the sum to it. It was the a over 1 minus r. Well, I'm going to use this fact here in trying to represent this function as an infinite series. If I want to represent this as a summation of something, well, if you look, I'm going to put right next to it the summation formula. So this is a very contrived problem here. It looks like very much like the geometric series summation formula. So in this case, my a sub 1 is actually 1, and my r is actually going to be just x. So if I want to plug that into the summation formula, you do that first term, 1, times your radius, which is x, raised to the n. So this infinite series for 1 over 1 minus x is x to the n. Now, let's talk about where this converges. We know that it converges using our limit test. The limit as n approaches infinity of x to the n plus 1 over x to the n. The absolute value of that has to be less than 1. If you simplify that, we've done this problem enough, you see that the n's go away, and that I'm left with just plain old absolute value of x, so the limit doesn't matter because there is no n's left. So we see that it has a radius of 1 where it converges, and it converges somewhere between -1 and 1. Now I don't know about these endpoints for sure, so let's go ahead and erase that for a minute. Somewhere between -1 and 1. Now notice this is centered at 0. I can tell it's centered at 0 because this is plain old x here. So to figure out the endpoints, if you recall how we did that, we put -1 in for x, and we see that this one here is divergent because it's -1 plus 1, -1 plus 1. And then if I put a 1 in for x, we see that one's also divergent because it's 1 plus 1 plus 1. So it doesn't include the endpoints. So what we did, we came up with a infinite series for this function here, but it only works between -1 and 1 and not even for the endpoints. Now that was centered at 0. If I wanted to come up with the infinite series centered around another number, say -1, it's a whole nother series. So now let's look at 1 minus 1 over x, 1 over 1 minus x, and now we're going to center at -1. Keep in mind that our goal is to make this look like this eventually, some a over 1 minus r. Well, if I want it centered at -1, then this had better be an x plus 1 in here, because remember that it's what makes it 0 and where it's centered. But I'm not allowed to just randomly add a plus 1 to something. So if what I really did is I subtracted 1 to this whole problem. So you notice if I add 1, I have the same numerical value as the function I started with. Do your little pre-algebra here. You have -x, so if you do this, you have negative x minus 1 plus 1 simplifies to back to where we started. All right, now I'm going to manipulate this a little bit. I'm trying to ultimately make it look like this. So we have 1 over, I'm going to leave that minus x plus 1 here, and this is a 2. 1 plus 1 is 2. Well, it doesn't quite look like this. That has a 1 minus r, so I'm going to factor out a 2 on bottom. It's going to leave me with 1 minus x plus 1 over 2. And you can check with distributive property that we factored that right. Well, this is dividing by 2 is the same as multiplying by 1/2, so I'm just going to put that 1/2 up there over 1 minus x plus 1 over 2. Now you notice now my a is 1/2 and my r is x plus 1 over 2. So putting this in my infinite series from 0 to infinity, my a is 1/2 and my r is x plus 1 to the n. And I've now written it as, x plus 1 over 2. Sorry, x plus 1 over 2 to the n, because that's my r. All right, you can then do what the other things we've looked at and find the radius of convergence and stuff like that to that series. All right, let's look at another example. Let's look at 4 over x plus 2. Let's center this one at 0. And I'll remind you what we're trying to do. We're trying to make this thing look like a over 1 minus r. So first thing I might do to this, I'll just do it one step at a time, is I might flip that around, 2 plus x. And once again, we need a 1 minus r, so that's the same thing. I might factor out a 2, makes that 1 plus x over 2, which is, that is 4 divided by 2 is simply 2. So it's 2 over 1 plus x over 2. We're almost there. I need that as a minus, so that is 2 over 1 minus a negative x over 2. So my a sub 1 is 2, my starting place, and my radius is negative x over 2. Put it in a summation formula. We get n equals from 0 to infinity of that 2 times negative x over 2 to the n. You can leave it like that. What you're going to notice is anytime you have a negative inside here, that's really negative 1 to the n times 2 is a multiplier. I can just pull it out of there, over x to the 2 to the n. So when you start evaluating this for where it converges, then you can then treat it as an alternating series. But either one of these, certainly on an open-ended test, I would accept. All right, let's center it someplace different. Let's look at 1 over x centered at 1. So if I want to center this one at 1, my goal is to make it look like a over 1 minus r. So it's 1 over x. Now I need a centered at 1, so I'm going to say plus and a minus. And let's see what we have now. If I rewrite this one now, I have 1 over 1 minus, I'll just write it 1 second, 1x minus 1. So I haven't changed the value of it. Now you see that the function's that. Well, I need to now write that as a 1 minus, so it's minus a negative x minus 1. And that's, you can see that that's the same value. Well, with that said then, the summation is n goes from 0 to infinity of, in this case, my a is 1, so I don't even need to write that down. The radius is negative x minus 1 to the nth power. And we can see that we're going to create an alternating series, negative 1 to the nth, x minus 1 to the nth. And then you can evaluate that. All right, that's a very specific case, and that's how we can turn rational expressions into things that are power series, and we use this formula right here. All right.